So I should open this today's seminar. First of all, good morning and also probably good evening, everybody. Welcome to this lecture series of Dark Energy in Dark Age, organized by APCTP. Today we have very special speakers, and this is our great pleasure and also honor for our center to have Professor Adam Riess Adam Riess as a speaker of today. And although I am a condensed matter theorist, I admit the cosmology and astrophysics is always the most fascinating discipline of fundamental science. And I also know that this field made very impressive progress in the last 20 years. And for this big progress, Professor Adam Riess made a big contribution by himself. In collaboration with the other people, of course, yes. So it is our honor and the pleasure to have Professor Adam Riess to speak about the forefront issues and ideas of our understanding of our universe. And this is a great opportunity to have him here. And I would like to welcome Professor Adam Riess, and I would like to invite him again to our center physically as soon as possible. And with this, I would like to, with this, I'd like to hand over session chair to Dr. Colgáin. He's organizing this great lecture series, and please.
Actually, Adam, I just had a quick, Adam, do you just want to run through your talk, or are you going to field questions?
I would take questions. Should we do the?
You're going to encourage people to break it up, and we'll have some discussion. And
you know, we could do it either way. I mean, I would probably, you know, if I ran through my talk, it would be 40 minutes, and then that would leave 20 minutes for questions. If you want to do it that way, it could be hard to get people's attention through Zoom sometimes. I don't know.
Okay, so let's see how it progresses. So I'm going to basically say that, you're free to ask questions, and we're very pleased to have Adam Riess, who has basically shocked us, well, in collaboration with various other people like 20 years ago. And he's also doing work at the moment that's essentially polarizing the community on the Hubble constant. So I'm going to let you take it away, Adam.
All right. Well, thank you very much for listening to this talk. I apologize I can't be there physically. I'm going to tell you about recent progress in measuring the expansion rate of the universe using observations of exploding stars called supernovae, pulsating stars called Cepheid variables, and various geometric distance measurements like parallax. If you want to read a recent review of this work, I can suggest this one listed on the lower left by Verde, Trejo, and myself. Our team's latest work is best summarized in this paper listed just below that. And this is work on behalf of the SHOES team. Okay, let me start from the beginning, especially if there are condensed matter physicists there, and remind you, one of the only ways we can learn about the composition, age, and fate of the universe is by watching it expand around us. We know the universe to be homogeneous and isotropic on large scales, and that plus the use of general relativity allows us to derive an equation of motion for the universe, really a differential equation that describes how the scale factor, the size of the grid that you see here, how that changes with time. That's on the left-hand side of the Friedmann equation, in response to the gravity of the universe and the geometry of the universe, which is contained on the right-hand side. Now, cosmologists would like to measure this function A as a function of time, the left-hand side, to learn about the interesting physics on the right-hand side. We cannot directly observe A or T, but we can observe proxies for both of these. For A, the scale factor, we observe redshift. That's a direct consequence. It's just the inverse. of A, the stretching of the wavelengths of light because of the expansion. And instead of measuring time far away, instead we measure distances, and through knowledge of the speed of light, that is as good as measuring time. And so by measuring distances in redshifts and measuring further and further away objects to look at the past, we can essentially learn about the function A of t. Now, it used to be that cosmology was simpler when we thought the universe was matter dominated, in which case you only needed to really measure the first two derivatives of A to learn pretty much everything you wanted to know from the right-hand side. The first derivative of A is, of course, the Hubble constant. It's the rate at which the universe expands, the present rate at time now. And this sets the size scale and age scale for the universe. A few decades ago, this was debated to a factor of 2 to be somewhere between a 20 billion-year-old universe that was very slowly expanding or a 10 billion-year-old universe that was quickly expanding. And much progress was made there. The next derivative, the second derivative of A, is the deceleration parameter of the universe. In a matter-dominated universe, there's a simple relationship between how much matter there is and how much deceleration. And by measuring the deceleration, you could learn what the mass density of the universe was, which would also tell you the ultimate fate of the universe, much like determining whether a rocket has escape velocity by measuring the deceleration of the rocket, but also the mass of the Earth. Now, the 1990s was really, I would say, a special time for measuring both of these quantities because of the availability of very long-range standard candles. So let me tell you a little bit about standard candles. So a standard candle is any object out in space whose luminosity you understand or can calibrate or standardize so that you can measure the distance to that standard candle just from its brightness. And I'm going to be focusing on two kinds of standard candles in this talk. The type 1a supernovae, these are exploding white dwarf stars that approach the Chandrasekhar limit by living in a binary system. These reach a peak luminosity of about 1 billion solar luminosities, so we can see them very far away. And then a more common but less luminous kind of standard candle, a Cepheid variable. This is a pulsating star, a supergiant star, and it's constantly overshooting hydrostatic equilibrium, and the frequency or period of the pulsation relates to the inverse of the density of the star, which scales very closely with its mass and luminosity. So there's an empirically calibrated period luminosity relationship that standardizes these candles. And in practice, these may not be perfect standard candles, but through the use of empirical relations motivated by theory, these have been standardized also by the use of measurements of the colors of the light of these standard candles. We also are able to account for dust along the line of sight to get very precise distances. So going back to the mid-1990s, two important samples for first measuring the expansion rate of the universe with type 1a supernovae. The most important probably was the Kalan-Tololo survey from the south, the points in green here. And then in my own thesis, the data points you see in red collected in the north. So through the use of CCDs, which were relatively new at the time, an empirical relationship between the light curve shape and the luminosity of the supernova, and accounting for the reddening or shift of colors due to dust, yielded very precise distances, good individually to about 6%. Of course, these are relative distances. If you want an absolute distance, then you need to run a tape measure out to a type 1a supernova. That's very difficult to do. And so the problem of generating or turning these into absolute distances and measuring the Hubble constant sort of lagged behind the ability to measure relative distances. I will say more about that. And also just to remind you, we often use the magnitude system. It's a logarithmic system for flux or distance. Every 5 magnitudes is a factor of 100 in brightness or a factor of 10 in distance. So even without knowing the absolute luminosity or absolute distances to type 1a supernovae, we can still measure further out and see how the expansion rate of the universe has changed with time. That is, we can go after measuring the deceleration parameter. And as I'm sure many people know, about 20 years ago, my colleagues and I measured distant type 1a supernovae at redshift of about 0.5, or a look-back time of about 5 billion years. And comparing those two nearby type 1a supernovae, we're shocked to see that the expansion rate of the universe is not decelerating. Instead, Q naught, the deceleration parameter, is negative. That is, the universe is accelerating as though you had something similar to what Einstein called the cosmological constant. That is, the best fit to the data was really a mass density of 0.3 and a cosmological constant of about 0.7. So still the magical combination of 1, but with a very large component of dark energy. Now, at the time, even though 2 teams had come to this conclusion, we worried if we were somehow being fooled by the supernovae. And so an important test of systematics was to go out to even greater redshifts, where if there was some astrophysical effect, evolution or gray dust or something, causing distant supernovae to look faint, then that should change as you go to even higher redshifts, where the universe would have been more compact, and therefore omega matter would have been the dominant term. The universe would have been decelerating. So it would follow this white line you see here, not the continuance of some kind of dimming. So over the next decade, teams went out and measured many more supernovae to improve the statistical measurement. And I led work using the Hubble Space Telescope to extend the measurements to redshifts of 1 to 2. And so after 10 years, about 1,300 type 1a supernovae were collected, so that you have to bin the data now to see. And what we saw was very clearly the signature of the accelerating phase now due to dark energy, and the decelerating phase earlier due to dark matter, as well as much higher precision, enough so that we could tell that indeed the dark energy looks like the cosmological constant, or lambda, to about 10% precision. I'll say more about that in a second here. So it's remarkable now, here 20 years after that discovery, to look at the best supernova data to date, and that's probably from the Pantheon sample, which is a large compilation collected by my former graduate student, Dan Skolnick, which sits, right in the center of the discovery contours from 20 years ago. But now, of course, the evidence is much stronger from this. Of course, as well, the thing that convinced the community is the many other measures unrelated to supernovae in the omega matter, omega lambda plane, the cosmic microwave background data from Planck you see here in purple, the baryon acoustic oscillation and other large-scale structured data that all converge to this location that you see here. So although the evidence is quite strong, the physics is still quite mysterious. Why is it that the universe appears to be accelerating? And we generally parameterize that by saying we don't know the equation of state of the dark energy, the thing whose negative pressure produces the kind of repulsive gravity in general relativity that causes acceleration. So one option is we have a true vacuum energy in the universe, what we call the cosmological constant, in which case the equation of state will be -1 at all times. This is sort of a consequence, if you will, of quantum mechanics that predicts a constant energy of empty space, but there's a terrible mismatch between the quantitative statement and what we actually see. So instead, it could be a dynamical dark energy, that is a field in space whose potential energy only looks temporarily like a cosmological constant. Of course, a third possibility is a modification to general relativity, that as we go to the longest ranges or the horizon scale, that we're seeing a breakdown of general relativity. It might be possible to tell this is going on because we would see different kind of equation of state of dark energy on different scales, on the scale of the expansion or on the scale that structure grows. So how do we proceed in a situation when we have these three options? Well, it turns out the easiest and probably most sensible way to proceed is to assume option one, because it's the easiest thing to calculate. It's the only one of the three options that is extremely well defined. And so we then look at any other experiment we can do, and we can use option one to predict what it should look like. And then we can look for departures. We look to see if essentially we can break lambda CDM. So the rest of this talk, I'm going to talk about that test, what I think of as the ultimate end-to-end test for lambda CDM. So as I said, we start with this new standard model of cosmology, lambda CDM, that has 6 free parameters and a number of ansatz. And we use that model as it would have for recombination at redshift of 1,000, where it would have been dominated by dark matter, neutrinos, atoms, and photons. And we use the model as it would have looked then to predict the physical size of fluctuations in the early plasma, the foremost being the sound horizon, the distance that a fluctuation can travel from the Big Bang until the universe becomes transparent. Also, the baryon density can be predicted from the model at early times. Then we observe the angular size of those fluctuations, either from the cosmic microwave background, or we can try to measure the primordial omega baryon. And in those steps, in making those measurements, we are essentially calibrating the free parameters of lambda CDM. And then we allow the physics and our description of the model to evolve the universe forward in time, like you see here, until the model itself evolves in its proportions to be mostly dark energy and dark matter. We get some checks on the expansion history along the way. I like to think of these as guardrails. Baryon acoustic oscillations and high redshift supernovae, even without absolute distances, relative distances show us, for example, the acceleration that I talked about. And finally, starting from the Big Bang and with this now calibrated model, calibrated from the early universe, we can predict the actual expansion rate of the universe today. And that's done to very high precision with the Planck data, 67.4 plus or minus 0.5. So a very powerful end-to-end test of this whole story, particularly powerful test of dark matter and dark energy, whose physics we don't really understand but dominate the universe, is to measure the expansion rate today to comparable precision. And so my colleagues and I started a project now about 15 years ago called the SHOES project to do just that, to produce the best direct local measurement of H0 and to try to reach percent level precision. And we thought we can do this by building what I would call a strong but very simple distance ladder, using geometry to calibrate the luminosity of Cepheids to measure their distances, and then to calibrate the luminosity of type 1a supernovae. We thought we could do better than the previous or first generation of such measurements by reducing systematics by 2 particular ways: by collecting data consistently across the ladder. I'll say more about what I mean there, as well as by making observations in the near infrared, which has other advantages. Also by thoroughly propagating the statistical and systematic errors to get realistic uncertainties. This project has been going on for about 15 years. We've gone through about 17 cycles with the Hubble Space Telescope, 17 proposals, and about 1,000 orbits. So it's been quite a lot of resources that have been dedicated to this. All right, so let me walk you through the distance ladder measurements. In principle, a distance ladder is the simplest thing you can imagine because it really doesn't even have physics in it. It is just empirical and really is extending geometric measurements, but it's critical that those measurements are consistent. So we start at what we call the first rung. This is what I joked about running a tape measure out. We actually measure geometrically a number of different ways, but you can imagine parallax to nearby Milky Way Cepheids. So this is what we call the anchor step, and this is done at distances of kiloparsecs to megaparsecs. Then in step 2, there are galaxies which have hosted type 1a supernovae nearby, and we use the Hubble Space Telescope to look for Cepheid variables in those galaxies. That's done at distances of 10 to 40 megaparsecs. And then finally, step 3, type 1a supernovae way out into the expanding universe, where the distances and their redshifts are used to measure the expansion rate of the universe. Now, a couple of important factors in a distance ladder. It's important to note there's really no astrophysical modeling whatsoever. This is all done completely empirically. There's really no use of general relativity. This often confuses people, but because objects like supernovae and Cepheids are co-located, we don't care anything about the metric between us and them. It's just that they're at the same location, so one calibrates the other. And there's really no use of lambda, the standard model of cosmology, because this is all done at very low redshifts or very small look-back times. Typical redshift is more like 0.05. However, it's critical to observe, measure, and utilize objects that are very similar, really as overlapping as possible across the distance ladder, which means, you know, these Cepheids here or these type 1a supernovae. So I'll say more about that in the talk. So let me start with geometric measurements. If you took Astro 101, you're used to thinking of parallax, which is sort of the gold standard of geometric measurements. The problem is that typical Cepheid variables in the Milky Way are pretty far away. They're a few kiloparsecs away. And so the parallax angle becomes very small. How small? Well, you know, we're talking about angles that represent a shift in the position of stars over the course of a year by about 1/100th of a pixel on the Hubble Space Telescope. So that's pretty difficult to measure. Really, it's almost, you could think of it as a centroiding problem. You're looking at some star compared to distant stars, and you're trying to observe that star moving back and forth over the course of a year, but it might be moving back and forth only 1/100th of a pixel, and we can only centroid a star to about 1/100th of a pixel on the Hubble Space Telescope, and so that wouldn't give you a very good measurement. However, my colleagues and I developed a new technique for measuring very precise parallaxes using the Space Telescope, and that is by spatially scanning or drift scanning the telescope as you make the measurements. And so these points turn into lines, and now you're measuring the separation between two lines is much easier because there are many pixels involved in these measurements. So if you're having trouble understanding what I mean, literally the stars go flying by and you get these parallel lines, and you measure the separation between pixels in the lines to much higher precision. This is what a little patch of one of those images actually looks like. Then you go in and you extract these scan lines column by column, and you line them up. And when you line them up in time, you notice that there's a kind of a noise in the direction along the scan. It's not really noise. This is jitter of the telescope. The telescope is bouncing along in the direction perpendicular to the scan. And so you're seeing identical jitter for all stars because they live on the same telescope, or they are seen by the same telescope. So then you subtract these lines in order to measure the separations of stars, and you get this nice smooth line, and then you get to average over thousands of pixels. So with this technique, we can get to 20 to 40 micro arc seconds. And so we did this for a number of years, and we measured the parallax of 8 of these Milky Way Cepheids, these long period Milky Way Cepheids. This back and forth motion you see is every 6 months on observation. So the amplitude of this back and forth is the parallax, the inverse is the distance. And this gave us a 3% calibration of the Hubble constant just 2 years ago. Meanwhile, we observed many more Cepheids, just their photometry or their fluxes with the Hubble Space Telescope, and combine those with parallax measurements from Gaia, which is a European Space Agency mission measuring parallaxes of 1 billion stars. And the combination of Hubble for the flux measurements and Gaia gave us another 3% independent calibration. We hope to get this to better than 1% by the end of this year. This is now the third parallax technique.
Can I ask a question? Was there a discrepancy? Did you find any discrepancy between Gaia and your scanning technique?
No, we did not. In fact, that's shown right here. So here is the period luminosity relationship. From Gaia is in purple. From our spatial scanning technique are the points in blue. And there was a prior technique to use the fine guidance sensor on the Hubble Space Telescope. This could be done for very nearby Cepheids, of which there were only a handful. Those are the data points in orange. So the three techniques give a pretty consistent calibration of the period luminosity relation. But now critically, we have observed these Cepheids with the same telescope that we're using for the extragalactic Cepheids. And so that nullifies the 0-point errors. And when Gaia reaches its final precision, we really should be able to get this to about 0.4%. Now, parallax is really only one way of measuring geometric distances to Cepheids. There are two other techniques I want to briefly mention besides parallax. There's a technique called detached eclipsing binaries, where in another galaxy like the Large Magellanic Cloud, you time the transits of one star orbiting another star, and by measuring the radial velocity and the time interval between eclipses, you are measuring the physical size of the star. And then by measuring the color of the star and the surface brightness, you can use a relationship for giant stars calibrated by interferometry to measure the angular size of the star. So you have a physical size and an angular size that gives you a distance. And that's been done geometrically for about 20 stars in the Large Magellanic Cloud, where there are lots of Cepheids. This is good to about 1.2%. And the third technique is the observations of water masers. These are clouds that orbit right near a supermassive black hole in the galaxy NGC 4258. The distance to this has been measured to about 1.5% through 10 years of VLBI measurements. And there are lots of Cepheids in that galaxy as well. So there are a wide range now of ways to measure 1% level calibration. Now, step two, as I said, is to look at nearby galaxies which hosted Type 1a supernovae to go back and observe Cepheid variables in those galaxies with the Hubble Space Telescope. The number of such galaxies really is the rate limiting step now for measuring the Hubble constant. Any one Type 1a supernova is good to about 6%. And so that over root n is really the rate limiting step. So a few years ago, we had measured 19 of these to give the best measurement to that point in time. And we're now almost done doubling the sample to 38. This will give a complete sample of all Type 1a supernovae within a redshift of 0.01 that live in the kinds of galaxies that host Cepheid variables. And these accrue at a rate of about 1 to 1.5 per year. So once we reach the sample of 38, it will be difficult to ever double this or even really, increase it by 50% in the remaining lifetime of the Hubble Space Telescope. So here are the period luminosity relations for the Cepheid variables in the first 19 of these galaxies, as well as these anchor galaxies that I talked about, where we get the geometric distances for calibrating the Cepheids. Now, this is one of the most important steps of our measurements and why they're much more precise than past measurements. And that is because we are using the same telescope to measure the Cepheid variables, both in the anchor galaxies, where they're geometrically calibrated, and in the Type 1a supernova hosts. So the question of flux calibration or uncertainties there drop out of the problem. They're nullified because it's a differential measurement. We also take care to measure over the same range of metallicity and period. So again, it's just a differential measurement done without the need to know the absolute calibration of the telescope. And these are Cepheid variables stacked. These are, anywhere from 30 to 100 in each individual galaxy. You can see their light curves in these composites. And then finally, another improvement comes from making our measurements of Cepheid variables in the near infrared. In the near infrared, Cepheids are better distance indicators because you see through the dust better, and they have a much smaller metallicity dependence. This can be seen nicely in the Large Magellanic Cloud, where here in the optical, the period luminosity relationship can have quite a bit of scatter. But as you move your way up to the near infrared, shown here in blue, or the de-reddened version, in green, and the de-reddened version here in cyan, the scatter becomes extremely small, and so systematics are really greatly reduced there as well. The third step is to measure what we call the intercept of the type 1a supernova Hubble diagram. That is the characteristic brightness of type 1a supernova at a certain redshift. And that is the third piece that you need to complete the distance ladder. Then after that, it's a simultaneous linear or multilinear regression, combining all the measurements, the empirical linear relationships, and a regression matrix that describes the relationship between the data and these linear empirical terms. This determines two quantities: the absolute luminosity of a type 1a supernova and the intercept of the Hubble diagram come together to tell you the value of the Hubble constant. And so this is what the data looks like. It's really a three-step distance ladder. As I said, geometry calibrates Cepheids, and that's done with up to 5 different sources for that calibration. 19, soon to be 38, where we calibrate Cepheids and type 1a supernovae in the same location, and then hundreds of type 1a supernovae out in the Hubble flow. And so as of last year, our best effort at this yielded 73.5 plus or minus 1.4, a 1.9% uncertainty, which, if you remember the value from Planck, going back to the beginning of the universe, is about a 4.2 sigma difference. So, of course, this is very interesting to see a difference like this. Now, going back over this and asking, well, is this robust? The first thing to look at is what different sources of the geometric calibration would give you, basically the first rung. This used to be the hardest part of the problem. There are now 7 different, actually. There are the water masers in 4258, the detached eclipsing binaries in the LMC, and then 5 different ways of getting the parallax measurements. The old fine guidance sensor results I talked about, my own team's spatial scanning, our use of Gaia and 50 Cepheids whose fluxes were observed with HST, and then recently 2 more Gaia measurements that were made using the binary companions of Cepheid, so not the Cepheid itself, but its companion, or the clusters that Cepheids live in. Either of these gives different systematics with Gaia than other methods. You can see these all are very consistent and consistently above the Planck value. And so it's very difficult to look at the first rung and find a way out of this, this tension that we see. Then moving on to the other rungs, what you're really looking for is about a 0.2 or 20% shift to produce this in any one of these 3 steps, sort of what you see with the dashed line here. Now, we looked at many different ways of analyzing the data, different reddening laws, how you describe the amount of dimming for different kinds of dust, ways of rejecting outliers in the period luminosity relationship, whether to fit the relationship as a single slope or 2 slopes, how you fit supernovae, what kinds of galaxies you allow supernovae to be in your Hubble flow sample, only late type galaxies, star forming galaxies. You can see there are small variations which get folded into the systematic error budget. But again, nothing that shows any indication of getting out of this problem. Other questions I am frequently asked, could we live in a giant void? The void would have to be about 9% in the Hubble constant. The answer seems to be no. If you look at both large scale structure theory or the empirical type 1a supernova magnitude redshift relation, which goes all the way out to redshift 2, you only see room for changes at about 0.6%. Is the flux scale of HST calibrated well enough? And the answer is yes. In fact, the uncertainty due to the flux, the linearity of the telescope is about 0.3% in the Hubble constant. Excuse me, that's about across 15 magnitudes. Could Cepheid crowding compromise the accuracy? We have a paper on this most recently a few months ago showing the amplitudes of the light curves of the Cepheids themselves give the best constraints on crowding and show that there's negligible, maybe at the 1 or 2% level, but nothing anywhere near getting to the level that we're seeing. Is there a difference in the supernovae themselves at the 2 ends of the distance ladder, the galaxies at redshift around 0.05 and the ones at 0.01, and it's a very small look back time, but more importantly, we've looked empirically for correlations in the Hubble residuals, and these could change the Hubble constant by less than 0.3%. Again, we're looking for a 9% shift in the Hubble constant. So basically, year by year, we have been able to reduce the uncertainties by addressing the various sources of error. This is our full error budget for this distance ladder. And most recently, in the last few years, it's really been mostly on the anchor step, the use of more parallax measurements, detached eclipsing binaries, improvements in maser distances, and also the improved calibration of the Hubble Space Telescope. So just to get a little perspective on this, we're not the first people to find this just with the greatest precision at this point. People have been building distance ladders with Cepheids and Type 1a supernovae. In fact, this has been the most widely replicated approach over the last 20 years. Why is that? It's because really Cepheids have some of the best advantages. They have the longest range distance indicator for ordinary stars. They have the most independent 0-point calibrations. They're the one that you can consistently measure the photometry along the ladder. And as I said, they're the most tested. Here's about 20 years worth of measurements. Some of these are done by completely different teams. The Key Project measured their own Cepheids with their own photometry, different cameras on the Hubble Space Telescope, done at different wavelengths. Anything with a star here was related to our SHOES project. So many iterations of our project, but in many cases, people took our raw photometry and reanalyzed the distance ladder, including people from the Planck team. They've done different kinds of analyses, Bayesian hierarchical analyses. In fact, this is now so widely replicated. I've seen it now as a graduate student problem set problem in the astrostatistics class at the University of Toronto. You can see the values are tightly within the range of about 72 to 76, always very much in this range. So I don't think this is an analysis issue. Now, what about other ways of measuring the expansion rate of the universe? And so we had a conference last year at KITP to bring together people who are using other techniques to measure what I would call a late universe, a local measurement of the expansion rate. And so we represented techniques involving Cepheids to calibrate Type 1a supernovae. They were also using Miras, which are a different kind of star, to calibrate Type 1a supernovae, tip of the red giant branch. And some of these different ones are different ways of calibrating those objects. And then independent of Type 1a supernovae, surface brightness fluctuations, also I'll mention later in the talk Tully-Fisher being used as well. And then single rung approaches that do not use a ladder at all. Strong lensing from the Holy Cow team. I could say more about that later. And also masers directly out into the Hubble flow. The Maser Cosmology Project has now measured 6 of these masers. This was a paper earlier this year by Pesce et al. That measured those directly into the Hubble flow. So that's without any of the previous. So if you did a naive combination, you'd get something like 73 plus or minus 1, but that would be a mistake because particularly these Type 1a supernova distance ladders overlap. They have overlapping supernova data. And so the right thing to do is to produce a kind of a combination that's independent by taking one thing from category 1, one thing from category 2 because it's independent of 1, and then category 3 and 4 are independent of each other and from category 2 and 1, and then one peremptory challenge. One thing you could say, I'm just not sure, I believe a particular method. And so we formed all those combinations in this review paper, and you can see that you get anything from about 72.8 to 74.1 with very small uncertainties. You could play the same game in the early universe. That is, you don't just have to use Planck to calibrate lambda CDM to predict the Hubble constant. You could use other cosmic microwave background data sets, or independent of the cosmic microwave background, you could use Big Bang nucleosynthesis, measurements of deuterium abundance to calibrate baryon acoustic oscillations. And these consistently give a lower value. So this is very intriguing. You could form a matrix of all these differences in the Hubble constant, ordering them from most precise to least precise on the early side, most precise to least precise on the late side. You can then convert that to sigmas of tension, and then you could focus in on Planck, because of course, since it's the most precise, you're going to get the most meaningful tensions from that. And if you break that out into the different late universe measurements, things that involve Cepheids give anywhere from 5.7 to 6.3 sigma. Things that involve TRGB, 4.5 sigma to 5.3. MIRAs instead of either Cepheids or TRGB, no lensing, or no type 1a supernovae. So you can see it's very hard if you take a look at not just our data set, but the other data sets as well in totality to avoid this. What is going on? What's causing this tension between the early and late universe? I really don't know. There's been a lot of new physics postulated. Some of it looks more potentially successful than other parts. There's a pretty wide consensus that it's more difficult to solve this at late times by altering dark energy, because that would run into conflict with baryon acoustic oscillations or high redshift supernovae. That is, the universe looks like it's accelerating, and so it's hard to get away from the equation of state being close to -1. More successful is generally solutions that attempt to alter the physics of the early universe before recombination. They're basically changing the sound horizon or the definition by changing either the sound speed or injecting energy early on to expand the universe faster and cause it to become transparent earlier, shrinking the sound horizon. There are also ideas about creating small scale, mild nonlinearities or inhomogeneities in the baryon density before recombination. So theorists are having a lot of fun trying to think of solutions to this. The tricky bit is you can't run into or violate any of the very precise data, particularly at the short wavelength end of the CMB. It can be very difficult. For example, you could put a new neutrino in that would appear to solve the problem, but if it doesn't have just the right properties, it will conflict with the cosmic microwave background data. Just finally, to close out, I want to mention there are other developments that are worth keeping an eye on. There's another less significant but still intriguing early versus late tension, sigma 8, the clumpiness on 8 megaparsec scales. Very similar to the Hubble tension in that you can predict it from the cosmic microwave background, and then you can measure it locally, either with lensing and peculiar velocities. Both of them now independently are getting about 3 sigma tension from the Planck values, both in the same direction. So that looks very intriguing. And as I said, it's reminiscent of the Hubble constant tension. I mentioned about some recent Tully-Fisher results just in the last few months, just to catch up on latest developments there. Finally, in closing, people often ask me, you know, can we really believe this result if we don't have a physics-based explanation for it? And I guess I remind people there are many times in the past where we see something quite intriguing that is more empirically robust, though we lack still a physics explanation at the time. The precession of the orbit of Mercury, the solar neutrino problem, the missing baryon problem. Even today's explanation of why rotation curves are flat is really another way of saying, you know, what is dark matter? Where is it? How come we still haven't identified it in the lab? Or the accelerating universe. Another way of framing that problem, though, is why do we get a lambda that is so much smaller than the naive value from particle physics? And so I think we do well to pay attention to these empirical problems, not sweep them under the rug because we don't yet have the physics explanation for them. These are often some of our best clues moving forward. So our next part of this in the next few months to a year is going to be to more than double the sample. I said 38, maybe even up to 43 based on a new program accepted in cycle 28. And so you could look forward, hopefully in the next year, to a combination between Gaia data release 3 and the new measurements from HST getting to maybe 1.2%, maybe even getting close to 1%. We also expect more independent measurements coming in from LIGO, giving us another late universe approach. Various missions, DESI, LSST, WFIRST, Euclid, are all going to better characterize W of Z and H of Z. That helps either explain the tension or eliminate that as a source. Next generation cosmic microwave background experiments could find signatures of one of the possible solutions, early dark energy, which I described as this injection of energy at early times. So I would say stay tuned. My final thoughts, and the last slide here, is the discrepancy at this point. You could argue it's anywhere as low as 4 or as high as 6 sigma. I would say it's around 5 sigma. It really depends on which data combination you produce. Another way of describing it is there's really no late universe measurement with any precision, I would say, that is lower than any early universe measurement. So That's quite profound. It appears to be robust because it would require multiple independent systematics or catastrophes, I guess I would say, to avoid. I think it's very interesting, unless a priori your Bayesian prior on vanilla lambda CDM with no more wrinkles is already greater than 5 sigma. So that's something, you know, everybody has to search their soul about that one. I don't know. I as Newton says, feign no hypothesis. I think we should follow the evidence, and there is a lot of evidence to go over and look at. And of course, always remember to be humble, because the universe might be more clever than we are now. So I will end there, and happy to take any questions that you have.
Thank you, Adam, for a very interesting talk. So I guess we're open for questions.
Question?
Yes.
For the early universe data, is there any way to directly determine sound horizon?
Right. You know, you see the angular size of the sound horizon in the cosmic microwave background. Then you predict the physical size using your understanding of the early universe, basically integrating the expansion rate of the universe till the universe becomes transparent. So that's based on basic physics. It basically gives you that time interval and tells you the physical size of the sound horizon, which is about 150, 145 megaparsecs. Measuring the angular size and having the physical size gives you the distance and the expansion rate, everything you want to know. The problem is that calculation of the physical size. Do you have all the right physics in there? When you calculate that, you need to know, you know, how many neutrinos there are in the universe, for instance. Or, you know, you need to know if there are any inhomogeneities on small scales. And so these are the things we grapple with trying to understand, could anything in there explain what we're seeing? Some people have looked at another horizon. You can measure an earlier one, the equality horizon. That is, I think, interesting as well.
Okay, I see. Thank you.
I have one question.
Yeah.
So, Adam, with the increasing precision on the H0, which covers a small but significant redshift range in late-time cosmology, how well do you think you will be able to estimate Q0?
Oh, you know, the one helps the other one in the sense that, you know, Q0 really is a measurement of what the current expansion rate is relative to the higher redshift expansion rate. So, you know, the better we measure the local expansion rate, the better we do there. But it's not direct with H0 in the sense that there are these absolute terms that are critical to measure H0. But, you know, having worked on both of them now, I would say measuring H0 is easier than measuring Q0 because, you know, for H0, everything is done at low redshift. It's all in the rest frame. We don't have to think about look back time or evolution. We're measuring everything in the same band passes. Q0 is harder in that, you know, we actually have to compare supernovae over a fairly wide range of redshift and look back time and different band passes because of the redshift effect. So that's always more challenging.
No, I'm aware that measuring Q0 is much, much harder. Yeah. But how well do you think you will be able to do?
Right. Well, I think it's going to depend on these missions. W1st, Euclid, LSST. The expectation is to get to a figure of merit of 1,000, which really means to measure the equation of state to, I guess, 1%, and to measure the time derivative of the equation of state to 10%. So we're not really looking at measuring Q0 anymore, but rather the parameterization of W to explain Q0, of course. But Q0 is just a kinematic term.
Okay, so I raised my hand, but apparently I can talk just directly. This is Adam. This is Arman Shafieloo. Okay. Adam, I have two questions, one scientific and another one semi-scientific. The scientific question is about the calibration of these distance anchors. As you know, George Statue has been one of the people who criticized the calibration that have been done. And even recently, he was emphasizing on the discrepancy which one can see from the cepids of the Large Magellanic Clouds and the NGC 4258. Yeah. So I know that this is one system, one comparison, but when you see a substantial discrepancy, that can point out to a substantial bias.
Sure.
So have you guys done anything to clear this issue, or finding?
Yeah, let me explain this. So I don't know if you could still see my slide. These are 7 independent geometric calibration sources. The top one is NGC 4258. This is the one that gives the lowest Hubble constant at 72, and it has an independent uncertainty, independent of all these other ones, of about 1.5%. Okay, so 1.5% of 72. What's that, about 1? So that places it about 2 sigma lower than the bulk of the others, 2 sigma. Okay, so 2 sigma I would say is not significant when I have 7. Now, George said in a recent statement that he can make that 2 sigma 3.5 sigma if he sets one of our nuisance parameters, the metallicity term, to a value that it doesn't actually come out to be in the simultaneous analysis of the data. And so I don't think that 3.5 sigma is meaningful, because you're creating a new tension in order to produce that tension. I think the right number is the one you see here, which is 2 sigma. And I don't think that that's very noteworthy.
Okay, thank you. So, and my semi-scientific question is that, what do you think personally, or what do you speculate is the nature of the current tension? Do you think there is some, I know there is no clear scientific evidence, but what would you bet on? It would be a, problem with the CMB data, or it would be a, some new physics, or
fundamental new physics?
I think that, it is, it's a hard problem, no doubt. I think that from looking at it from my standpoint, the easiest or most productive way to solve it still looks like the early universe side, because all the early universe measurements sort of have a single point failure there, in that they need an accurate description of the contents of the universe at redshift of 1,000. That means, the number of neutrinos or relativistic particles, the state of the how homogeneous the universe is at those times, even a primordial magnetic field, anything like that is going to change potentially in the same direction. All of the early universe measures, the different CMB ones, omega baryon. And so, that's the one place where I would say the physics is still a little mysterious, and you can do it. I don't know how to do it in the late universe. I mean, it would have been easy if the dark energy equation of state came out to be minus 1.2 or minus 1.3, and we'd say, oh, that's it. That's pretty weird as well, because that's phantom dark energy, but at least empirically that would explain it. But, you could rule that out, minus 1.2 or minus 1.3 at, 3-4 sigma. And so you can't just trade one tension for another. So, I think the early universe looks interesting, but, it may not be the only way out.
Thank you.
Sorry, Adam.
I have a question. You have a question,
Marty. Can I make a comment before on Adam's last statement? So Adam, it seems to be, if you allow early dark energy, you basically have, you exacerbate cosmic shear, the tension in cosmic shear. Also, there's problems in large scale structure.
Yeah, so you're going to have to go back and look. There was a recent paper by the group that first came out with early dark energy that says that there's some misinterpretation of that large scale structure calibration. And so they argue that early dark energy has no problem with shear, or, sorry, when you say shear, do you mean sigma 8?
I mean sigma 8, yeah. So
it really does very little. It doesn't help sigma 8, and it doesn't hurt sigma 8. The large scale structure is right now, as I said, an argument between a couple of groups of whether large scale structure is impacted by early dark energy or is not. And so I'm going to direct you to, if you send me an email after this, I'm going to point you to the paper that came out maybe just a few days ago, arguing that it's not a problem.
Thanks. Marnie, you've got a question, yeah?
Yeah, going back to the early dark energy. Now, many theorists would like to associate that to a fundamental new neutrino scale underlying neutrino rest masses in quantum gravity. Now, that would solve the problem nicely, but of course, it immediately introduces the issue of altering perhaps the neutrino astrophysics. So what influence does that have on any of these models, like for eclipsing binaries? Would you know that?
Oh, you mean how would changing neutrino physics actually affect stellar physics?
Yes.
Oh, I've seen very few. There's maybe one or two papers where people have looked at, you know, what happens with like axions and instabilities in the cores of stars. I saw a paper recently by Capozzi et al. Testing this with a tip of the red giant branch luminosity, but I haven't seen people work on it very much from this direction. And the thing that is more difficult is to not cause inconsistency with the damping tail of the cosmic microwave background. So, for example, a basic neutrino, a sterile neutrino, would have to have certain kinds of interactions, self-interactions, I think, as I recall, in order to avoid causing a conflict with the damping tail of the CMB. This was a paper by, I can't remember. If you send me an email, I'm happy to send you the link.
Okay, I think there's a whole literature on that point, actually.
Yeah,
but yeah.
there is. There is. There must be more questions. Please don't be shy.
Yeah, can I ask one more question on LIGO?
LIGO, yeah.
So with your extensive experience on this measurement, what do you expect ultimately as a prediction towards LIGO? LIGO's measurement will be when they have sufficient number of Newton star coalescences.
Right. Well, first of all, let me say I'm very excited about LIGO. You know, everybody's excited about LIGO. It's just tremendous. And I'm optimistic that, you know, they will make good distance measurements. I would predict empirically that they will see the high value of the Hubble constant because, of course, they're a late universe measurement. So that's nice to make predictions, even if you're an empiricist. Now, having said that, you know, distance measurements are hard. And I think already we've seen, you know, it's taking LIGO much longer than they expected. You know, the kinds of systems they need to see, these kilonovae, look to be fairly rare. They still only have one from 2017. They're offline now, so they won't be back in the game until 2022. And then they need at least 20 or 30 to start, you know, weighing in with some precision. So I am not expecting LIGO to really, you know, answer this in the next 5 years, but eventually I expect they will make some contribution. It's just, you know, it's so hard to say. Every time LIGO shuts down, they try to improve their sensitivity. And, you know, it can be difficult to predict whether they have improved it or not, or by how much. And so a lot of that is, you know, very TBD. More questions?
Can I add one more theoretical question?
Please.
So when you think about, and this is a theory arena question, when you think about general relativity, one thing that, of course, is striking, that general relativity is a classical theory, and it has no hidden small energy scales, low energy scales in space-time. And of course, that is in some sense indirectly inherited by lambda CDM, because lambda CDM, you know, takes a very classical approach that is just characterized by one lambda.
Right.
But at the same time, we have an evolving universe, and of course there are scales. There are low energy scales defined by the size of the universe. In fact, if you like, by the cosmological horizon. And so far, this is not usually taken into account in the evolution of the universe. And at the same time, one can make certainly various arguments that should give, if you like, roughly a 10% correction to what you naively expect from lambda CDM. That, of course, would take us into the late time cosmological correction in addressing the tension problem. But it seems somehow you're somewhat skeptical about a late time, and I'm referring to a fairly very late time solution that plays out over a redshift, say, between 0 and 1. but it seems you're relatively, or maybe not skeptical, but reserved about.
Well, yeah, I would say the problem is if you look at the high redshift supernova data, it's so precise, and this is like, for example, in the Pantheon paper, if you look at the residuals, they so precisely track cosmological constant equation of state -1 that we don't see anything happening gradually along the way, if you know what I mean. And I'm not completely sure about the physics you're talking about. I don't know if you're talking about essentially inhomogeneities.
No inhomogeneities.
Okay, no inhomogeneities. Fine. Okay.
Homogeneities that gives you a dynamical lambda.
Yeah, then I would say that, you know, the problem is, you know, to my disappointment in some ways, the equation of state looks so close to -1, you know, it's -1 plus or minus 0.05. You know, to solve the tension problem, it needs to be more like -1.2, maybe -1.25. And so, you know, it's just the expansion history over the late part of the universe just looks so close to lambda that it just doesn't look like a way to find this 10%.
So maybe some of us should be looking into exactly how you are defining your W parameter, because when on your second or third slide,
yes,
you showed an expression, the first slide that shows W on your slides, that shows an expression that is actually based on a, if you like, modified lambda CDM model. You know, the 1 plus 3W times omega lambda plus, sorry, the 1/2 omega, if I do it by heart, 1/2 omega n minus 1 plus 3W. Yeah. Sorry, that equation. Whereas if you allow for low energy corrections, then actually the equation is quite different. And that is related to the notion that omega m and omega dark energy are correlated at the lowest energy scales. So if this is the equation based on which you calculate the W that you just referred to, then, you know, we might be talking about—
It's not, because this is what you see here is just a kinematic term, right? Q naught.
Yeah.
It's not what we measure either. We go back to the Friedmann equation. And so when we actually do the fits, we do it in terms of the Friedmann equation and the prediction of the true, you know, A of T or distance redshift relation.
Yeah, so there may be a problem there. That's also why I asked about your Q naught.
Okay, well, I mean, I've never heard, I mean, you know, this literature and these measurements have been around for 20 years. I'm not sure if you're saying something that's different than anything people have looked at before.
Yeah, it is not the same.
Okay, well, you should take a look and see whether, you know, the way, I mean, these papers are quite detailed, you know, the way they are calculating distances in the metric, and see if it factors in what you're talking about or not.
Hello, Adam.
Since there is not more question, I want to ask one more question. There have been some criticism, again, to some of the activities of the SHOES team, that the results are not reproducible. So it means that, you know, not all the data is available in a way that other groups can alternatively reanalyze everything and practically confirm what you guys derive.
Wow.
Is this really correct, or is it possible
that seems like a strange claim to make. As I said, in Joe Bovey's class at the University of Toronto, students are given the raw photometry of the Cepheids and the supernovae and the geometric distance measurements, and are asked to measure the Hubble constant themselves independently. I've seen Joe Bovey's solution set. So I mean, not only have there been dozens of papers reanalyzing the data, but if you can do this as a graduate student problem set, I'm not sure what information would be missing.
Okay, thank you.
Right? I mean, I would push back hard on that claim that there's anything missing from being able to fully reanalyze the SHOES results. I would flip it around and say, I wish I could reanalyze the Planck results. I mean, that's much harder, you know.
Okay, thanks so much.
Hello, Adam.
Yes.
Stephen here from APCTP. Thank you for the talk. I have a question. So your calibration measurements are at very low redshift, and they're below the homogeneity scale. So
when you say the calibration measurements, where Cepheids and supernovae are in the same galaxies?
Yes.
Yes.
accurate that they're below the homogeneity scale? So a few
Well,
hundred.
the homogeneity scale is irrelevant for them because this is what I was saying earlier. We only have to know that they are in the same location, right? So we are not actually using either general relativity or redshifts in order to get that calibration. All you're saying is, imagine you see in some galaxy that could be at any distance, you see a supernova and you see a Cepheid. And you know how bright the Cepheid is, so that allows you to calibrate the supernova, and they're at the same location. And so they're along the same, the same geodesic, if you will.
But have you assumed that the geodesic, the photons are traveling in straight lines? Because they
Right,
won't.
it doesn't even matter as long as they're traveling the same lines.
Okay, so that doesn't enter into the calculation at all. The fact that.
No, that's why I said it's quite a distance ladder is quite independent of general relativity or cosmology. It only assumes that two things are co-located in space.
Okay.
Do you see what I mean?
Yeah, but it's really amazing that so because you wouldn't expect the H0 you measure locally to be the same H0.
No, but basically you're measuring H0 from type 1a supernovae way out into the Hubble flow, but you are using geometry and co-location of objects in order to calibrate that, right? So, you could imagine this whole thing, I mean, a simplified version of it is to say, I've got type 1a supernovae in the Hubble flow to measure the Hubble constant, and let's imagine a type 1a supernova went off where the sun is. So you knew the distance to it, or, somewhere so close you can measure parallax to it, right? So that's a geometric calibration of something that you are measuring well into the expansion of the universe, all the way out to redshift 1 or 2.
Okay. Okay, thanks.
Hi, Adam, I have a question.
Yeah.
I was wondering, is there any directional dependence to any of these measurements, or can you?
Yeah, there's been a number of good papers on the isotropy of the expansion of supernovae. There was one recently from Dragan Hutterer's group, maybe Soltis is the first author. A few papers. I have not been involved in any of them. From what I could see from most of them, everything looks fairly homogeneous and isotropic. I haven't seen any robust claims of departures.
Okay, thank you.
I don't know if that's more or less it, right? We seem to have a number of questions, and Adam has answered them.
I'm happy to take any more questions if there are any others.
Yeah, can I ask one more question? You can interpret it any way you like, but it seems you're very successfully converging on a final, value of H0 that can be written in a stone. And so what are you going to do next?
I think it's going to take a couple of years to sort of, really finalize things. As I said, we're going to double the sample. I'd like to also continue with, we've put a lot of irons in the fire connected to Gaia, and Gaia is still in the process of really getting their best results. Gaia is nowhere near the precision yet that it will, it's advertised to end up with. And so that's all going to be extremely interesting. Of course, I'm always interested in, any other independent tests of this whole process. So right now we are using the Hubble Space Telescope to try to measure Cepheids all the way out to Coma, to skip type 1a supernovae and build a 2-rung distance ladder. We're also using type 1a supernovae, Cepheids directly in the Hubble flow from more nearby galaxies. And then I think it's getting more and more interesting to look at peculiar flows using supernovae themselves. So this is getting back to that sigma 8 question, but doing this with supernovae locally. So I'm quite interested in that. There's going to be all these great observatories coming online with, 1 million supernovae, LSST, W1st Euclid. So, I think there's going to be so much data and information. I'm quite excited about many of these different avenues.
Okay, I think that's more or less it. Well, thank you, Adam, for your time. Thank you for basically fielding a whole lot of questions. So there's be a lot of curiosity. And yeah, I mean, it's sort of interesting how the community is like, although you've given us lots of results, right? It really is polarizing the cosmology community. I mean, in astronomy, there may be more of a consensus on this.
Yeah, polarizing, and is it, you mean polarizing in terms of like, what is the solution? Is it systematics or is it physics?
So for example, I had a discussion at the weekend. I'm not going to mention names,
Sure.
but basically they were trying to convince me that you are now an outlier on H0. And basically Holly Cow, because Holly Cow have a recent paper that maybe they relaxed some assumptions and they got a result close to Planck. And then they mentioned like tip of the red giant branch and basically Wendy Friedman's results. So basically,
yeah. So let me here. I just pulled up the sort of sum of late universe measurements. So the more recent stuff with Holy Cow you were mentioning is they have explored if they, so up till now, they have assumed that their mass models follow a sort of conventional either power law or Navarro-Franken White plus stars. And that's, you know, they get very precise Hubble constant, very similar to our value. If they relax those assumptions about mass models, not being those conventional ones, then they could get a wide range of Hubble constant measurements. I would say they could get either the low or the late or early universe value. So that just becomes sort of inconclusive rather than, you know, telling you something. And then, you know, when it comes to the other measurements, let's see, I mean, you know, masers directly in the Hubble flow give, you know, 73.5 plus or minus, I don't know, 3 or something. There is the surface brightness fluctuations. There is the Myras. Tip of the red giant branch has a bit of a range. It is the lowest of the values, but you know, it's still higher than the Planck value. So as I said, there is no late universe measurement that is lower than the early universe sort of central value. And so I don't know how anybody could say you know, that they see us converging on the early universe measurement in the late universe when there are no values on the below it. You know, so no, I don't see it as I mean, in terms of outliers, I don't think, I mean, you know, my view of it right now is, you know, you've got a bunch of independent late universe measurements that range from 70 to 75. And you have early universe measurements that range from 67 to 68. I think that's just a straight up empirical statement of what we see. And, you know, how you interpret that, you know, depends on, you know, probably whether you have, you know, a strong feeling about lambda CDM being done, or, you know, whether you think that there might be some wrinkles left in that.
Okay. Well, thanks very much for that clarification. Okay, so I would just like to thank Adam again for a very interesting and stimulating and a very comprehensive overview of the various results on H0. So thank you.
Sure.